This session will look at the challenges of taking Oracle performance tuning theory and applying it in practice to a real life system. My name is David Kurtz. I work for the Accenture Encotech Group. I specialize in performance tuning. I spend a lot of time with PeopleSoft ERP systems, but I also look at a lot of other Oracle database systems, and I write about both Oracle and PeopleSoft on my blogs, and I've written a book about what happens when those two worlds collide. I'm also an Oracle ACE director, and that means I like coming to conferences and sharing the experiences that I have. You may wonder why we still have physical Oracle user group conferences around the world and that people go to them in such large numbers. I'm very lucky here in the UK that I've been able to go to the UK Oracle user group conferences now for probably 25 years. And over that time, I've got to see and learn from a lot of very good people. The kind of session that I like going to see most of all probably is where you deal with fundamental theory about the database or a particular feature. How does it work? What are the underlying mechanics? Because then I should be able to make some reasonable predictions about how it might work for me out in the real world. So the rest of this session, I'm going to take a practical example, a case study of a performance tuning project where we took a number of features and brought them to bear, and some of them worked as expected, and some of them caused us a few challenges. So I've chosen this particular case study because there were a lot of features, and at every feature we needed to understand how it might work and whether it would help us. And then sometimes you have a choice for how that feature is going to be implemented, because you can push a feature too far and then it starts to give you difficulties. And what does pushing it too far look like for each of those features? Some of those features might interact with each other, and there were times where we needed that interaction to work to get the particular effect that we were looking for. We're dealing here with a third-party application, so the application is set, there's lots of things we can't change. So we have to know how the feature will act with the application, and will the behavior of the application make the feature work. Perhaps we have to adjust the configuration of the application in order to make it work. So there's lots of different features. I've written about this before, and you'll find some more background on my blog. This case study is about a PeopleSoft financial system running at an insurance company in North America. We're going to be looking at their general ledger reporting that uses the PeopleSoft nVision utility. They're running on Oracle 12.102. It's a 2-node rack cluster running on supercluster. That's the Sun Solaris version of Exadata. Their performance objective is that their suite of about 600 GL reports has to run every night after the standard financials batch and must be complete before the start of the US East Coast working day. When you work on a performance tuning exercise for an application, you need to understand a bit about the application. Now, no one expects the DBA, in this case, to be an accountant or other financials functional specialist, but you're going to need to interact with the users to understand what they're seeing. So you need a common language that they can understand as well. And in this brave new world, the DBA becoming a data scientist, and I'm still not entirely sure what that term means. If you're working with performance problems, it means you're going to have to get involved with the application and with developers. But of course, if you're doing performance tuning, you should already be doing that. We can think of general ledger as a sort of data warehouse in the financial system. Every financial transaction creates or contributes to 2 general ledger entries. There will be a financial amount there, and there'll be various other dimensions. So there'll be the name of the ledger. You can have different ledgers for different reporting requirements or different legislatures. There will be the fiscal year and accounting period into which that transaction goes for reporting purposes. It'll have a currency, and there will be a number of other attributes that describe aspects of the business, the account, the department, the business, operating unit. It depends. We take account as an example. Every transaction goes into a general ledger account to say what kind of a payment it is. So you might, for example, have electricity, gas, oil, other heating costs. Each one of those will have an account, and you might report on them separately, or you might report on them as a group as energy costs. And that's a decision that you make in general ledger, and the different reports are reported on different parts of the business at different granularities. Now, general ledger is a typical example of data put into data warehouses, and some companies do actually extract their general ledger into a fully fledged data warehouse. But then it takes time for the data to get from financials to the warehouse. And accountants love to have a real-time view, especially at month end. You know, they might put through an adjustment journal to move costs from one account to another. And then as soon as they've done that, they want to rerun the general ledger report and see the effect of that adjustment. So they want to do their reporting on the OLTP system. So in PeopleSoft, we've got fact tables, which are the ledger table. We have a budget ledger, where your budgetary information goes, and you might report the actuals from ledger against the budgetary values to see if you are inside budget or not. And we also have summary ledgers, and this is a sort of performance optimization in the application. The summary ledgers look a lot like the ledger table, but they have fewer rows, fewer columns, and the data will have been summarized, so it will be less granular. They'll all have these dimension columns, and the business dimensions are hierarchical, so that accounts and the like can be rolled up. That hierarchy in PeopleSoft is held in a data structure that PeopleSoft calls a tree. And I'll talk a little more about that soon. Before I can talk about performance tuning, I have to talk about instrumentation. Before you can fix performance problems, you have to measure what's going on. You need to know how much time was spent doing what. Now that's more than just what SQL statements and what execution plans and what wait events. It's extremely useful to know where in the application a particular SQL came from. Instrumentation is about adding application context to your other Oracle performance metrics. Oracle has provided a PL/SQL package procedure called DBMS application info, and it sets and reads various session attributes. In particular, the set module package procedure sets the module and action attributes, and they are then picked up by the ASH and AWR data. This is something that you have to build into your code so that as the application executes, the module is set to give you the location of where you are in the program. And PeopleSoft added that to their code. You have to turn it on by configuration. And when you do, while you're in the online part of the application, you get the name of the component and page that you're currently executing. And if you're in an application engine batch program, the action is set to the program section step and step type. So you get the address in the application where the code comes from. Now, unfortunately, COBOL, SQR, and nVision was not instrumented by PeopleSoft. And when an application is not instrumented, you may have to get creative. So Batch processes in PeopleSoft are initiated by the process scheduler. It's a bit like the concurrent manager in eBusiness Suite or the job scheduler in the database itself. And the first thing a PeopleSoft process does when it gets started is it updates the status on the process request record to say, I'm processing. It sets the status to 7. So I can create a trigger on that table that fires when the status is updated to 7. And then I have a PL/SQL procedure that sets module to be the current process name and action to be the process instance number, the unique ID of the process request. And it also stores the process instance in a package global variable that I can read back later. So now I have instrumented my batches so that if they're not otherwise instrumented by PeopleSoft, I know exactly which process is running, and I can go and look that up on the process request table. With nVision, I've had to go a little further, and I've used fine-grain audit and a fine-grain audit handler to enhance the instrumentation further. Now in nVision, one report book can run several reports. And the first thing that happens when a report starts up is it queries a parameter table. So I've created a fine-grain audit policy on the query on that parameter table, and the custom PL/SQL fine-grain audit handler reads the parameters from that parameter table, and I can obtain the name of the report, the layout ID, and the business unit that it's running, and I can add that to the action. So now I can see which report within the report book is running. I can see the process instance number, report ID, and business unit in action in my ASH data. So here I have one process instance number representing one report book that ran 4 separate nVision reports, and I can see the name of the 4 reports, and they ran across 2 business units. And I can then drill into that data and get all of the SQL for each of those reports and know which SQL came from which report. I found it helpful to index the fine-grain audit log because I needed to query it to get the parameters back out of it. I also recommend that you pretty regularly and aggressively purge the fine-grain audit log table, and I also agree with Oracle's recommendation to move AUD$ and the fine-grain audit log dollar table out of the system table space into another place per this Oracle note. Now I've instrumented my ASH data, I can profile it by report and layout. The instrumentation created a relationship between application context and things like SQL and plan hash value and so on. So I can look for particular reports, for statements, execution plans that take the most time. I can look within all of my nVision reports and identify which report. I can look at a report book and look at which report within the report book is my problem. Or I can look at a specific report, all filtered by action. This is the kind of SQL I have to write to profile the ASH data for nVision. I like using subquery factors. It does actually make the SQL more simple and easier to read, and the processing flows from subquery factor block to the next subquery factor block. So it starts with me deciding which reports I'm interested in dealing with. So I get that from the PeopleSoft table PS, PCS, RQST, and I can get from there to the specific ASH data by time, module, and action. And then I left out a join to the SQL text table to see if I've captured the SQL text in AWR, because I need to get a SQL text and a execution plan. I add up the amount of time by counting the number of ASH samples. I can count the number of executions, And then I can use analytic functions to say which SQL accounts for the most time within a process instance and a force matching signature. I can get the name of the table that was being queried from the execution plan if it was captured. Then I get a report like this. This is for one particular report book, and it's grouped by force matching signature. So this is the force matching signature that accounted for the most time, a little over 12,000 seconds. There were 2 execution plans, and those are the top SQL IDs for each execution plan, and the top one is one of 3 SQL IDs that produce that SQL execution plan out of a total of 60 executions and a total execution time of 11,720 seconds. And I can see that it queried one of the summary ledger materialized views. So now I can tell which statements I have to look at first when it comes to performance tuning, and you work down this profiled list of statements. Let's look at what the application is doing. nVision is a sort of plug-in into Excel. The output is an Excel sheet. It's most commonly used in General Ledger, and in General Ledger it's like a data warehouse of financial information. You have financial amounts and you have various business attributes, and most of those business attributes have a hierarchical character, and that hierarchy is held in PeopleSoft trees. You also have time attributes like fiscal year and accounting period. If I was to draw a data model, it would be a sort of star schema with ledger at the center. The dimensions in the application are not joined directly to the ledger table because they're combined with that hierarchical data and extracted to tree select tables, and those tree select tables are then joined to the ledger table. Fiscal year, accounting period, and currency, they don't use tree select tables, they're just filter conditions. This is a fairly typical piece of nVision SQL. It was generated by the nVision tool from the report definition and configuration. It's not something that a programmer writes, and there's no way to reach in directly and change it. We're using the ledger table as a fact table here, but we might have used a summary ledger. There are 3 dimension tables here, 3 tree selectors, and these were populated with the data that I need from the attributes and the hierarchy definitions. We're using tree select 5 here because it's a 5-character attribute. The other 2 are from tree select 10 because they're 10-character attributes. An nVision query will always specify the name of the ledger, the fiscal year, and the accounting period. Here accounting period is a range 1 to 11 because it's a year-to-date query, but it might also say accounting period equals something. Every tree selector has a unique identifier that can be used to identify the data extracted. And this one joins to business unit, so I can tell that L1 is the business unit dimension, and then L is chart field and L2 is account. Note that it's the tree selectors that are joined to the fact table, not the attributes that extracted them. There are other filter columns at the bottom. You normally see currency, and it's normally not very selective because each ledger is only one currency. We aggregate the financial amounts on ledger. Notice that we group by the tree node num on the selector. That's the hierarchical information, not by the attributes business unit, chart field, or account. So we're now left with a non-trivial problem. The tree selectors are populated at runtime, and you can have many different selectors on different trees on different ledger dimension columns in the same selector table. We get static selectors. The whole tree is extracted once and it's left there until the tree changes. What normally happens is every month they bring on a new tree. Or you have dynamic selectors where just the bit of the tree you're interested in reporting on is extracted for every time the report runs, and then it's deleted when the report ends. So it's a very dynamic thing. One of the problems is you can get debris left behind if an nVision terminates abnormally without clearing out its selectors. The application does not maintain optimizer statistics, and normally each of the trees are quite heavily skewed, so the data tends to be skewed, and with different trees extracted into the same tree selector, the data will be all over the place. So it's very difficult to define statistics that accurately describe the data in a tree selector and then produce desirable execution plans. And then finally, you end up searching the ledger table by varying combinations of different attribute columns. Let's look at what we can do about this problem, and let's start with some easy stuff first. Partitioning. Partitioning has been available in Oracle since 8.0. It's only available on Enterprise Edition. It's a cost option, and you can partition in up to 2 dimensions only. So this diagram was taken from the Oracle manual. On the left, table 1, the table is not partitioned. All the data from January to March is all mixed up together. On the right, the same data has been partitioned into 3 partitions for January, February and March. If I want just the March data, then in table 1 I have to look through the entire table. But on the partition table, providing my SQL says where partitioning column is March, then Oracle will only look in the March partition and it will prune or discard the January and February partitions. So partitioning can save me work and I/O and time if the partitioning matches my application. When it comes to fit partitioning to an existing or third-party application, we need to look and see how that application accesses the data. We need to look at the SQL that it uses. This is a piece of SQL from nVision, and all nVision queries on the ledger tables will have an equality predicate on ledger and an equality predicate on the fiscal year, and you'll either see an equality predicate on accounting period or, as in this case, a range predicate. So these are good candidate partitioning columns for nVision. Now, most customers use monthly accounting, so they have 12 accounting periods. You'll also see period 0 for brought forward amounts, and you'll see periods 998 and 999 for carry forward and adjustments. In the new version of the app, you only see 995. So what I normally do with ledger is that I like to range partition it on the combination of fiscal year and accounting period. That's 2 columns in one range. And then I create 14 periods per year for this year, last year, and for any future year. And if there's data prior to that, I normally put it into annual partitions. And I take the same approach for the ledger, ledger budget, and any summary ledger tables. I can also subpartition the data. And your choice of subpartitioning column depends on the data. Ledger itself is often a very good candidate, and in this case study, that is actually what we did. We had 3 main ledgers, so we created single value list subpartitions for each of them, and we had a default list subpartition for any other values. At other places I've taken other decisions. I've once partitioned by business unit. It was a multinational system, and they had 6 sets of regional processing that ran at different times of the day, and 6 sets of regional reporting that ran at different times of the day. So we created a list partition for the top business units in each region and a default partition for the rest. And that meant that financial batches that were updating the ledger in one region didn't bash into reporting processes that were running in another partition. So partitioning kept the processing away, so we avoided read consistency. We can also have different subpartitions in different partitions for different fiscal years as the distribution of business units changed. Now in this case study, we didn't subpartition the summary ledgers because they're single ledger summary ledger tables, and there were no other columns that were particularly good for partitioning. Because we're on an engineered system, we can use hybrid columnar compression without needing the advanced compression license. So we can introduce it at the same time as we partition the ledger table. But we cannot compress data that is updated in conventional path mode, only that which is written at create table time or inserted in direct path mode. So previous years are compressed query high because they're then much smaller and they're not referenced very often. Last year we compress query low because we get improved performance from that. But current and future partitions cannot be compressed because they will be written to in conventional path. Once we introduce partitioning, we have to maintain it. Each new fiscal year will require a new set of partitions on each of the partition tables, the ledger tables and the summary ledger tables. My preference is not to create a max value partition. Thus, you have to create the new partitions before you use them, otherwise you will get an application error. So this forces you to put a process in place to put them in place in good order. The alternative is to introduce max value partitions so that you don't ever get application errors. But the risk there is that you forget to create the new partitions, and also it makes the process of adding the new partitions more difficult because you either have to repeatedly split the max value partition or you have to exchange it off, drop it, add the partitions, and then add any data in the old max value partition. As partitions become historical, the application ceases to write to them. So you have the opportunity to rebuild them and squeeze out all of the free space to pack the data, and you can also at that point introduce compression or hybrid columnar compression. And for previous years, we might coalesce the monthly partitions into single annual partitions, and we might also increase the compression level from query low to query high. We may also choose to collect and lock the stats on the newly rebuilt partitions. And of course, we have the opportunity to archive and purge this data by either exchanging or dropping the old partitions. Where we do have indexes on these tables, they are mostly locally partitioned, so they don't really provide any problems for management. One exception is that the unique index on the ledger table remains a global non-partitioned index, so you have to be careful that your index maintenance operations do not invalidate it, and if you do, you have to rebuild it. Once you introduce partitioning into a system, you are usually facing into a world of manual scripting. Now, in PeopleSoft, the partitioning challenge has become so frequent on so many different systems that I've actually got to the point where I've created a utility to generate the partition DDL. Now that's all very well for a third-party app like PeopleSoft where you work with it at many different customers. But if you're just introducing partitioning into one system, you are probably facing into doing this manually. Slightly surprisingly, these two features go hand in hand. This system uses summary ledger tables for some of the GL reporting. Now, these are smaller reporting tables defined and maintained by the application. They're like the ledger table, but they have fewer attribute columns, so you get more aggregation and fewer rows of the table. Therefore, they're smaller and faster to work with. They're maintained by an overnight process that incrementally refreshes them. It's all beginning to sound a bit like a materialized view, and in many ways they are quite similar. But I can't simply replace them with a materialized view because I can't express their content simply with a single query, and because the behavior of the summary ledger maintenance process is actually controlled by application configuration, and that might change over time. And then even if I could reflect the summary ledger as a single query, that would have to change to keep up with the configuration. And therefore, because these tables are maintained with an application that writes in conventional path mode, I can't introduce hybrid columnar compression on them. But what I was able to do was simply to build a materialized view on the summary ledger, creating an exact copy of it. Now, I found it was easy to use a pre-built table and then reference that in the materialized view. We introduced a daily full refresh of these materialized views to run after each summary ledger refresh, done as a part of the batch window. And therefore, that materialized view refresh was done in direct path mode. We didn't need a materialized view log on the summary ledger, so the summary ledger refresh was not impacted. The materialized view had no free space reserved. It was also partitioned by fiscal year and accounting period in exactly the same way as the corresponding summary ledger tables. We didn't find a good candidate for subpartitioning. And we were also able to introduce hybrid columnar compression on the materialized view with query low. And we didn't bother to build any indexes on the materialized view because we were only interested in doing smart scan on them. We enabled query rewrite on these materialized views so that when the nVision reports query the summary ledger tables, the Oracle Optimizer automatically considers rewriting the query to reference the materialized view. To make that work, we had to set query write integrity to either trusted or stale tolerated. And then the optimizer would naturally rewrite them because the materialized view is very much smaller. It's not indexed, so it will only consider smart scan. And for such queries that really needed to use an index, well, we'll stick with the indexed summary ledger table. At this point, I should also talk about Bloom filters. Bloom filters have been part of Oracle since version 10. They're named after an American mathematician, Burton H. Bloom, who came up with the concept of using a bitmap to pre-filter data before you actually did an exact hash match, so that the hash would be smaller. So all of the values in the join column on your probe table are pushed through a hash function, and the hash value maps to a bit in a bitmap. And for each hash value that you get, you set the bit to 1. And then you take that bitmap and you pass it to the probe on, say, your fact table. And you push all of the join values on that table through the same hash function. And if the bit for that hash value is set, then that's a possible match. And if it's not, it's definitely not a match and it can be thrown away. You may get false positives because you may have multiple values that produce the same hash value. And what this does is it filters down the data very quickly through a full scan before you then have to do an exact match in the hash join. And because that's very much smaller, it's very much faster. Hence the name of the original paper, Space-Time Trade-Offs in Hash Coding with Allowable Errors. There are some excellent papers and presentations by Christian Antognini about Bloom filters. The reason they're so interesting on an engineered system is that the Bloom filters are pushed down to the storage cell. So your data is filtered very quickly during the initial smart scan before it is then hashed together on the compute server. Now, Bloom filters only work on equality joins. So what this means is that how you build your application SQL really matters. It has major consequences for performance. Well, in PeopleSoft nVision, the tree performance options affect the SQL that is generated. Let's look at our hierarchical accounting data again. Accountants like to group and roll up related data for reporting. So let's take a very simple set of chart of accounts. This isn't a PeopleSoft example. Transactions are allocated to different GL accounts for reporting purposes. And what you find is that related and similar accounts are often grouped together. So I have electricity, gas and oil, 7200, 7201, 7202, etc. But they may be grouped together in a range 7200 to 7299, which are energy fuel costs. And they in turn are part of general overheads. So it depends what you want to report on. You may want to report on individual accounts, or you may want to report on all of your energy fuel costs. It depends what detail you want to show in your reports. In PeopleSoft, this hierarchical data is extracted into the tree selector. And each node in the tree selector, each row, may either represent the range of accounts, or it may represent the individual accounts, depending on what kind of tree selector you've selected. And that has consequences for the SQL that's built later on in nVision. So that a ranged tree, you'll get a count between, but in a single value tree, you get a count equals range. Well, if I want a Bloom filter to work, I've got to have a count equals range. It won't work on a count between. That means to get the performance benefit of the Bloom filter on the full scan on the engineered system, I have to choose an option that will give me single value trees. Tree selectors come in two forms. Static selectors, the entire tree is extracted into a tree selector and it remains extracted until the tree changes when it is extracted again. The report reports on the parts of the tree of interest by specifying which nodes on the tree with tree node num between criteria. So the SQL changes each time. And you always get a count between criteria, never equalities, because the underlying attribute might change at a different time to the tree. But if you choose dynamic selectors, then only the part of the tree upon which you wish to report is extracted into the tree selector table at runtime, and it's deleted again when the report completes. I can also choose to force the selector to contain only single values, even if the node on the tree is a ranged node. So thus I will always get a count equals range. And this is the option I need if I want my Bloom filters to work. In my nVision queries, some of the trees can be used to just filter by a dimension, and some can be used to filter and group. So here, these two dimensions are not referenced in the group by clause, so they are only there to filter. There is an optimization in PeopleSoft to replace this with a list of literal values that are in the tree selector. And we find that this works very well on Exadata because the predicates are pushed to the storage cell up to about 1,000 literal predicates, beyond which the time taken to evaluate the predicates becomes quite significant. And we find that this optimization is far less effective on non-Exadata systems. So the nature of the system you're working on will change the optimization decisions you make for the same application. It's finally time to talk about optimizer statistics. One thing's for sure, if you don't tell the optimizer the truth about your data by providing it with accurate statistics, you really can't expect it to produce a sensible answer. The trouble is that occasionally, even if you do tell it the truth, it may still not produce a sensible result. So you need to gather stats at the right time, and that means doing it in the application if needs be. So in PeopleSoft, there's a piece of the language called update stats. And on Oracle, what that does is it calls DBMS stats for a particular table at runtime, either online or during a batch. And it's a broadly sensible approach. You see the same thing in Oracle eBusiness Suite with the fund stats package, which is essentially a wrapper for DBMS stats. It's interesting that in Oracle 19c on Exadata, we've got a couple of new features, real-time stats and high-frequency automatic stats collection. And they're there to plug the gap between the application changing the data and the statistics needing to catch up. And I talk about that in another presentation. Maintaining stats on the ledger tables is fairly straightforward. Financial batches insert new rows as they post. They mostly work row by row, and nVision doesn't alter the contents. So we generally find that the overnight maintenance window is adequate for maintaining the stats. The summary ledger table statistics are updated by the batch process that builds them with the update stats macro that we talked about. And the summary ledger materialized views, well, they collect real-time statistics because they're populated by direct path load. I find it useful to have histograms on ledger on low cardinality columns, up to 254 distinct values really. I would prevent the collection of histograms on very high cardinality columns where you've got more than 1,000 distinct values. So things like posted total amount, and for us, project ID and operating unit, they had too many distinct values. In 12C, you can use top N histograms and they work better than high balanced. But perhaps for all the other columns, you just say, I don't want histograms. And you would control this by setting a table preference. It's very tempting to have histograms on fiscal year and accounting period, but be aware of this bug. Don't do this unless you also have extended statistics with histograms on the combination of fiscal year and accounting period, because it really won't get the cardinality right. The tree selectors present a very different challenge. We have to use dynamic selectors in order to get equality joins between the selector and ledger tables so that we can use Bloom filter on the ledger tables. So we've got lots of concurrent reports running, generating lots of selectors, so lots of rows being inserted into and deleted from the selector tables. Each selector is given a unique selector ID number which is allocated sequentially. And statistics are not maintained by nVision reports at runtime, and we can't introduce code into nVision to do so. So over time, the selector number goes outside the range of statistics until the next maintenance window. And we've got different extracts from different trees for different attribute columns, all mixed up in the same selector tables because they have the same length. One of the early things we tried was optimizer dynamic sampling. So we tried not having explicit statistics on the selector tables, and we tried locking and deleting the statistics. And we got inconsistent results. Essentially, the problem was that the optimizer couldn't decide which selector to start with, because you wanted to start with the smaller selectors and work up. But without a histogram, it didn't know which one was smaller. We also tried turning optimizer dynamic sampling up to level 4, and then we ran into a parse problem when we were using literal values, because the huge number of literal predicates increased the parse time. Now I have to say at this point, the new 19C features on Exadata look very interesting. Real-time stats are designed absolutely to deal with the problem where column predicates go outside the range of the statistics by keeping that statistics range up to date. And certainly high-frequency automatic stats collection will help by bringing the stats up to date more frequently. But today we're back on 12.1, so we can't use them. And also, very little of this helps when you have lots of trees which are extracted into the same selector table, because even with accurate statistics, we found it was very hard to get the optimizer to make the right decision. So we came up with the idea of interval partitioning the tree selector tables on selector number with an interval of 1. So each selector has its own partition. Every query on tree selector has an equality predicate on the selector num. So you get single partition queries. And that means that it can use partition level statistics to accurately describe the selector. Now, we immediately ran into trouble with this approach. It's quite complex to build and to implement. You have a maximum number of partitions of little over 1 million. And if you have an interval partition table defined in this way, then you also have a maximum value on selector number of the same. So we found that there's a need. We got through the selector numbers in about 4 or 5 months, so we need to reset the selector number in the application every 3 months. And the other problem we ran into is that this is an abuse of the feature. Interval partitioning is just not designed for this frequent creation of new partitions in the same table. We got massive problems with library cache locking. Essentially, only one process can insert a new partition into the same table concurrently. And we've got multiple concurrent nVisions inserting rows for different selectors into the same selector table. The workaround we came up with was to create multiple copies of the tree selectors in multiple schemas and synonyms of grants to make the rest of the application work. And then we have a trigger to set current schema to one of the schemas containing one of the sets of copies. And we used a hash function on process instance to choose which schema. And in the end, we built up to 32 schemas with 32 copies of the tree selector tables, so that concurrent processes were unlikely to be populating rows in the same schema at the same time. And this did significantly reduce the library cache locking. But I think probably this is what happens when you abuse a feature. You have to do a second workaround, the multiple schemas, to evade the problem of the first workaround, the interval partitioning. We wrote some code fired from triggers to do selector usage logging. It started out as additional instrumentation so we could see what was going on, but it very quickly became an essential part of the solution. Had we used static selectors, PeopleSoft has a system based on version numbers to determine whether the tree has changed since the selector was extracted, and there is a control table which holds all of this. But dynamic selectors are not tracked in any way because they're created and deleted. Although one of the problems is if the nVision report crashes, you get debris left behind. So we created a logging table, and we created some compound triggers on the tree selectors, which counted the number of rows being inserted, and after the insert statement, logged that to a logging table. We also collected information about the session, the module, action, and the client info. And then we found that we could use that log table to determine when rows were left behind in the tree selectors by a crashed nVision, and we also used it to drive statistics management. Our logging table built up to have, over time, to have all kinds of things in it, not just the number of rows, but the module, the action, the client info, a status flag to say whether the rows had just only been inserted, whether they were for a static selector, whether they'd been deleted, or whether the partition had also been dropped. We extracted the tree name from the library cache from the SQL. We logged the schema we were in and also the partition name. We created compound triggers on each of the tree selector tables. We have an after row trigger that counted all the rows being inserted and also tracked the min and max values on the range. And we did all of this in memory with package global variables so that there is no physical I/O. And then we have an after statement trigger which wrote those values to the log. This is a sort of poor man's real-time statistics because it's much of the same information that track with the 19C feature. There's also a corresponding delete trigger because you need to track the data value being deleted in the after row trigger. You can't see it in the after statement trigger, and then we maintain the log in the after statement trigger. Selector logging drives a selector purge process. We tidy up after the process so that we drop partitions after they're no longer required to free up space. We did try having a trigger do this purge when the nVision completes, but it actually aggravated the row cache lock problem. So instead we just have a daily purge process which clears up after any terminated nVisions and any online nVisions after 2 days because they can't possibly still be running after that long. We don't purge the selector log because it contains useful information about what's been going on in the application, about report, usage, tree size, and tree usage. And this is a report on the selector log, and you can see information about different trees. So this account tree joins nearly 8,000 rows on some occasions. So this is an example where we don't use literal value optimization. This tree always joins 2889 rows. So we always join the whole tree and it's not selective. So even not just because it's quite large, we again only join it, we don't use literal values. So we can use the tree selector log to decide which application optimizations we're going to use. Sometimes it's quite difficult to make tree performance option decisions for the whole suite of nVision reports, and we've had to override it for specific reports. The other thing that tree selector logging does is it drives statistics collection on the tree selectors. We realized pretty quickly that you can't collect statistics in a DML trigger because gather table stats includes a commit, and you can't commit in a trigger unless it's an autonomous transaction. And if you try to do it in an autonomous transaction, then you can't see the data that's been inserted that fired the trigger because it's in a different transaction and it hasn't been committed. So you get invalid statistics. So that didn't work. So we tried to submit a database job to the database job scheduler to collect the statistics on the partition. And we used DBMS job submit to do so, so that the request record only became active after the insert that fired the trigger committed, and then the job on the job scheduler could also see the data. Well, that was partially successful. We certainly did get accurate partition statistics that did generally produce some pretty good execution plans, but we found it could take a little while for the job to start, and the first few queries would run with no statistics on the partition and might produce poor execution plans. So then we realized that we knew everything about the table from the selector log. We knew how many rows had been inserted for a given selector. We knew the min-max value on the ranges. We know that the values are unique. We know which partition it's in. And we can make a pretty good estimate about the number of blocks and the clustering factor. So it's actually possible to mathematically calculate some pretty sensible partition statistics and then to update them using set table stats. Although it still has to happen in an autonomous transaction, but that doesn't matter because I don't need to reference the table data. And we found that that worked pretty well for us. Although in testing we found it was better if we still also submitted the database job through the scheduler. There's no doubt that properly collected real stats were better than our calculated stats, but our calculated stats were better than no stats at all or optimizer dynamic sampling. Up to this point, I had resisted introducing SQL profiles because of the continuously mutating SQL statements that you get with nVision, although the use of dynamic selectors and single value joins has actually simplified and stabilized the SQL significantly. And we were left with a few problem statements for which I did use SQL profiles, but not perhaps in the way you're expecting. Most of us will be familiar with Carlos Sierra's XFR SQL profile script. It takes a full profile of hints from a captured SQL execution plan and converts it into a SQL profile that then can be applied back to the statement and stabilize the execution plan. SQL patches were introduced in 11G and they've been formally supported and documented in 12C. And they work by injecting a set of hints into a particular SQL statement. And they match by SQL ID, so it's the exact match of the SQL statement, there's no force matching. But you can do exactly the same thing with SQL profiles, and you can make it force match, so that similar SQL statements with different literal values will all match and be treated in the same way. And we did that with nVision, and our favorite hints were rewrite to force the materialized view rewrite to occur, px join filter to make the Bloom filter occur. We used the leading hint to force some of the tree selector tables to be processed first before visiting the ledger table. And on some occasions we introduced parallelism too. And we found this was a way of stabilizing the few problem statements that all of the other techniques that I've already discussed didn't quite address. We also set certain database parameters just for nVision. We didn't want to set them database-wide because that would have had impacts database-wide on other processes that we didn't want to test. So we had a data-driven method using a trigger that fired when the process started to set certain parameters that could be set at session level. For example, we wanted to disable skip scan for the nVision reports, but I didn't want to go back and test it across the system. And that's the end of our story. Every decision we made along the path for tuning this system, every feature we introduced, required that we had a reasonable idea of how it worked. Now, in some places, I think you might justifiably criticize the complexity. The library cache locking on interval partitioning is perhaps a good example of pushing a feature too far. It didn't work quite as we expected, but we stuck with it. In my defense, I would say that the GL reports on this system are now available at the start of the business day in continental Europe. So the business got what they wanted and then some. Almost everything that I've discussed, I got the ideas from other people, from working with them, from reading their blogs or books, or going to their presentations at conferences. So go out there and be curious. And good luck.